Dear viewer, welcome to our program for today, your program of Knowledge Quest on Hope Channel Kenya. Our subject is physics, and today we're going to look at a new topic. I'm glad you have tuned in, and you are going to learn a lot. I'm your teacher, Peterson Maranga, and I want to welcome you. Feel free, sit, and let us learn together. Today we are going to make an introduction to a topic known as measurement. And we're going to take some time here, and so we are in a topic known as measurement 2. In our physics course, it is in Form 2 physics, a second topic, and so measurement 2. Now, when we see measurement 2, it means we have already covered measurement 1, and measurement 1 was covered in Form 1, and so there are things I'm going to assume and really expect that you know. And such things include basic quantities. Basic quantities are things which we must have covered elsewhere earlier on, and so we're going to make an assumption that you understand about them. And we in Form 1 must have been told that quantities are categorized into two. We had basic physical quantities. We also had other quantities known as the derived physical quantities, and there are examples, of course. And so at this level we may not really go into them, but now in measurement 2 we're going to look at, if you learned of measurement 1, for example, let's talk of a quantity like volume. We talk of another quantity like density. These ones were covered much earlier. Volume is the amount of space occupied by a substance. Density is the ratio of the mass of a substance to its volume. And now in measurement 2, we're going to look at something slightly different. That suppose you have calculated the volume of a given substance, and now you have obtained the value, but then you are to express the answer in a given according to some given requirements. For example, you give the answer in standard form, or you give the answer to 2 decimal places, you give the answer to a given number of significant figures. Those ones we did not discuss earlier on. We only looked at how to find the volume of a given surface, how to find the density of a given substance, how to find the area of a given region, but we didn't really bother or take much time to discuss on how to express the answer that you have obtained. So that now in measurement 2, we are going to find the same volumes, we're going to calculate the same density, we're going to measure the same time, we're going to measure the same masses and find the same weights as we did earlier on. But now we're going to express the answers according to some given specifications, probably according to specific significant figures, to a given number of decimal places, to give the answer in standard form, etc. And so now I want to introduce us to the following. Number 1, the significant figures is where I want us to start from in this measurement 2. And we are going to look at some few rules that will guide us in how to express the answers that of the calculations we did in measurement 1. Now, when we talk about the significant figures, what are we referring to? Now, when we talk about significant figures, let me give us an example of a number. Say we have 6, 8, 7, 9, 2. Can have a 5 there. This is 687,925. Suppose we have calculated the area, assuming, and we have such an answer. Now, when you talk about the significant figures of the number that we can see here, the significant figures, we are referring to the number of digits that we can see. Digits, digits are the numbers from 1 to 9. So we have 1, all the way to 9, they are called the digits. Now, when we talk about significant figures, we are referring to the number of digits which are written in that number. For example, when we look at this, is 6 is the first digit. We have 8, all of them are digits, so they are 1, 2, 3, 4, 5, 6 of them. So we can say that the number we see there is written to 6 significant figures. So significant figure simply refers to the number of digits which are appearing in a number, the number of digits. So that if we were to write that answer to say 2 significant figures, now our first significant figure is the first number we see from the left. No, this number is 687,925. The first significant figure, the first number from the left is 6. Then this is the second number, the third number. So this is 1, that is the second, the third, the fourth, the fifth, the sixth. So that our first significant figure is 6. The second significant figure is 8. The third one is 3. The fourth one is 9. The fifth one is 5. The sixth significant figure is what? Is the 5 that we are seeing there. Now, when we are going to get the answers from the calculations as we did earlier, our now expectation will be that you can give that answer, you can express the answer to given significant figures. And before we come up with that one, let me just give us the significance of a 0. The significance of a 0 when it is used in a number. That is what is very important for us to note. Now we have the following rules to note. When 0 appears 0 to the left of a number, 0 to the left of a number is not significant. That is very important for us. If 0 appears to the left of a number, then that 0 is never significant. But then the 0 is a placeholder. It is just used as a placeholder. For example, if I write a number, say 0.26 or 0.00, there's a decimal point there, say 7, 3. This 0 is not a significant figure. It's just used as a place value holder. These 3 zeros you see in the second number, 0, and this one and that one, 0.00, all these 3 zeros you can see there to the left of the first 90 number, and so all of them are not significant. And so number 1, we say that when 0 appears to the left of a number, that 0 is never, it is not significant. It is just used as a place value holder. So that now when we're giving it in terms of the place values, this is the ones to the left. We have the ones, the tens, etc. But now to the right we have the tenths, and then we have the hundredths. And so then the 0 is just used as a place value holder. The same thing happens for the second number. Number 2, 0 between non-zero digits is always significant. 0 between and 0 digits is always significant. For example, if I have a number, say 1, 4, 0, 5, that 0 is, because it is between 4 and 5, the 0 is significant. So that now this number is written to 1, 2, 3, 4 significant figures. But the first 2 numbers we wrote earlier, because the zeros are not significant, because they are to the left of a number, then the first significant figure here is 1, is 2. The second one is 6. This number is written to 2 significant figures. For the next one, we have all these 3 zeros are not significant, and so the whole number is written to 2 significant figures. That is when the 0 is to the left of a number. Already we have talked about that. Now, when the 0 is in between and 0 digits, that 0 is always significant. And so that if we have 1,405, the 0 is between 4 and 5, which are non-zero, so the 0 is significant. So then the whole number 1405 is written to 1, 2, 3, 4 significant figures. If we have another number, say 20008, all the 3 zeros, because they are in between 2 and 8, all of them are significant. So then this number is written to 1, 2, 3, 4, 5 significant figures. 5 significant figures. So if a 0 or zeros are in between non-zero digits, then those zeros are always significant. That is very important. So case number one was when a zero is to the left of a number, it was not. When it is between non-zero digits, it is always significant. And then we have the last case for a zero. We talk of a zero which is to the right of a number. Number 3, 0 to the right of a whole number. That zero, the unique part of it, that it may be or may not be significant. So there are two options there. If a zero is to the right of a whole number, that zero may be significant or it may not be significant. For example, if we have a number 1300, like that one, this number, the two zeros, because this is a whole number, the two zeros may be significant or not significant. So that it will be safe for us to say that number is written to two significant figures. That can be very correct. Another person can say it is written to 1, 2, 3 significant figures. That is also correct. Or we can say 1, 2, 3, 4, all of them are significant. It can as well be been written to 4 significant figures. So if it's a whole number and there's a zero to the right of it, the zero may be significant or not. So that if we use this as an example, then we can say if the two zeros are, if only this zero is significant, then the whole number is written to 3 significant figures. If both of them are significant, then the same number is written to 4 significant figures. But always 1 and 3 will be significant. Non-zero digits are always significant in a number. So then we cannot really talk about, we cannot debate about the first, that is 1 and 3. We can only talk about the two zeros. So if we were required to give the number of significant figures in this number here, say 8, 9, 3, 4, and then I put 3s or even 4 zeros there. Let me put commas. This is 89,340,000. We can say that the number is written to 1, 2, 3, 4 significant figures, and that can be very okay. That means the 4 zeros you are seeing there are not significant. Someone else can say that the number is written to 5 significant figures. That means you count from 1, 2, 3, 4, 5. It is only that zero which is significant. Another one can say it is written to 6 significant figures. That means this zero and that one are significant. It's also correct. Another one can say it is written to 7, meaning 3 zeros are significant. And another one can say 8 significant figures, to mean all the zeros which are in that number are significant. And all these are correct arguments. So we only say that if a zero is to the right of a whole number, that zero may be significant or may not be significant. So if we do a calculation and we get an answer like that one, and we are required to give the answer to 5 significant figures, we just count from the first significant figure we are saying, which is 8. So we have 1, 2, 3, 4, 5. So the answer will be 8, 9, 3, 4, 0. But we don't drop the other zeros for a whole number. We retain them. So we have the 3 zeros. So you see it is the same number. And so that number we are saying is written to 5 significant figures. If we were to write it to 6 significant figures, so we shall still count 1, 2, 3, 4, 5, 6. So we have up to there. We have our 8, 9, 3, 4, 0, 0. But then we do not drop the other 2. We have to keep them for a whole number. So you see it is still the same number. That's why we are saying a 0 to the right of a whole number may be significant or may not be significant. It depends on how you are required to express that answer. Finally, a 0 to the right of a decimal number. Number 4, 0 to the right of a decimal number, not a whole number this time round, a decimal number, e.g. say 4.960. A 0 to the right of a decimal number is always significant. So in this case, this number is written to 4 significant figures because this 0 is to the right of a decimal place. So we have the first significant figure. We have 1, 2, 3, 4. All the numbers that we are seeing there are significant, and so 4.960 is written to 4 significant figures. So we simply say that if a 0 is appearing to the right of a decimal number, then the 0 is always significant. So we have mentioned 4 things here. The first one, we said that if a 0 is to the left of a number, whether the number is whole or a decimal number, to the left of it, those zeros are not significant. If it is between and 0 digits, the 0 is always significant, whether it is 1 or more than 1 zeros. So they can be up to as many zeros as you can write. As long as if they are within or between and 0 digits, the zeros are always significant. If it appears to the right of a whole number, the 0 may or may not be significant. That is for a whole number. But if it is to the right of a decimal number, then the 0 is always significant. So if we have an answer like this one, 0.0034, and then I keep 2 zeros after the 4, these first 3 zeros are to the left of that number. So the first 3 zeros are not significant. That is where we started from. If a 0 is appearing to the left of a number, it is not significant. But now if you look at these other 2 zeros which are coming after 4, they are to the right of that number. So then these 2 are significant, but the first 3 are not. So the whole answer is written to 1, 2, 3, 4 significant figures. It is very important for us to note. And so we are trying to use the 4 rules we have mentioned about the zeros. To the left of a number, when we said in number 1 there, when we say that the 0 is to the left of a number, it simply means before and non-zero digits, if we may put it so. So if you look at this number, these 3 zeros, 1, 2, 3, they are before and non-zero, they are before 3. So that's why we are saying all of them are not significant. But when you consider the other 2, they are to the right of a decimal point, and so they are significant, the 3 of them. And so finally, before we do examples, all the non-zero digits, all non-zero digits in a number are always significant. These ones are significant. So if we have non-zero digits in a number, wherever they appear, whether it is to the right of a decimal point or to the left of a decimal point, those non-zero digits will always be significant. This is very important for us. So we're going to do a few examples of writing different numbers to different significant figures, and we shall be making use of the 5 rules which we have written or we have talked about. So questions: express the following numbers. Express the following numbers to 3 significant figures, all of each one of them. So number 1, we have this one here, 0.00862, say 4, then 5. We want to express that number to 3 significant figures. So what do we do? For us to express it to the first 3 significant figures, we need to know where the first significant figure is. The first significant figure in a number is the first non-zero digit. We count from the left. So all these zeros already we know they are not significant. The non-zero digit we have there is 8, so it is the first significant figure. Then we have the second one is 6, the third one is 3. So if we wanted 3 significant figures, we count 1, 2, 3 of them. So we shall be having 0.00862, but we don't just stop there. We consider if this is the third significant figure, we look at what is coming after it. If it is 5 or more than 5, we add a 1 to this one. But now if we look at this, we have 2 and 4. 4 is less than 5. We cannot add 1 to this one. We just drop the other 2 numbers so that the answer becomes 0.00862. We stop there. Now if we have another number, let me give a whole number, number 2. Let me have the positive of the whole number of it, 6245. We express the same number to 3 significant figures. We still do the same counting as we did before. The first significant figure is 8, so we have 1, 2, 3 of them. So if this is the third significant figure, we consider the next number which is appearing there. If it is 5 or more than 5, we add 1 here. But we see this is 4, 4 is less than 5, so there's nothing for us to add. So we shall retain the 2. But now this becomes 862. If it's a whole number, we do not just drop this 4 and 5. In their places, we keep 0. So we have 2 zeros after that number. This expression is slightly different from the one we had previously for a decimal number. You see, for a decimal number, we did not keep these zeros for 4 and 5 because already we know if we keep those 2 zeros and they are after the decimal point, the 2 zeros are going to be significant. And so the whole answer will be to 1, 2, 3, 4, 5 significant figures instead of 3. And so that is why for a decimal number, we just dropped them. We did not keep zeros. But for a whole number, we count 1, 2, 3. So we have 862. In place of 4 and 5, we keep zeros. We don't drop them. They have to be there. And now if they are retained, they become place value holders. They are not significant, yes, but they are place holders. They have to be included. Number C, let me have a number like this one. 8, 0, 6, 5, 6, 7. We are expressing, let me have 0.2. We are expressing that number to 3 significant figures. So what do? We still count the same thing. We have the first one, the second, the third. So we want up to 6. But now what is coming after 6 is 5. 5 is, from what we already said, if it is a number after the one we need is 5 or more, we add 1. So because it is 5 itself, we shall add 1 to this 6. We get 807. But now we are going to keep the zeros for 5, 6, and 7. So we have 3 zeros. These 2, 3 zeros here. Then after the decimal point, we do not write anything. Why? Because if I make a mistake of writing that decimal point there, then that 0 is significant. If it is significant, then these other zeros are also significant. The whole number becomes written to 1, 2, 3, 4, 5, 6, 7 significant figures and not 3 significant figures. If I wanted only 3 after the decimal point, I do not write anything. So I have 807,000. Then I keep the 3 zeros to stand in for 5, 6, and 7. So they are just place value holders but not significant in themselves. And that is very important for us, so that next time we're going to do calculations of what we did in measurement 1, and in the other topics we can express the answers to the required number of significant figures without much problems. Only for you to remember that if the major concern here is for a 0. If it is to the left of a number, that 0 is never significant. If it is to the right of a whole number, it may or may not be significant. If it is to the right of a decimal number, the 0 is always significant. Between non-zero digits, they are always significant. And then all the non-zero digits in a number, of course, they have to be significant if they are appearing in that number. That is the first thing for us to learn in the measurement 2. The next thing for us to discuss or to have a look at is the standard form of numbers. Writing numbers in standard form. Standard form becomes very important when we have very big numbers or very small numbers. For example, if we have the mass of a particle in the air, a particle of dust, say its mass in the air is 0.00000 and another 0, 1, say 2 kilograms. That is a very small value. This is 0.123 zeros, 1, 2, 3, and another comma, then 1, 2 kilograms. That value is so small that at times it is more convenient for us to express the value in standard form. Or suppose we wanted to obtain the mass of a very big object, for example, a planet, and then we have the mass is 3, 6, 4, and then 0, 0, 0. 0.0000000, something like that, 1 kilograms. Now this is the opposite of what we already have. These are very big mass, and also for us to use it in the calculations, it's always conducive and convenient for us to express such values in standard form. The standard form becomes much simpler and more convenient way of writing numbers. Now the question, how do we write numbers in standard form? How do we reduce them to something that is more convenient for us to use, probably in the calculations or in the expression of the answers? Now, a standard form is in such a manner that numbers are written in standard form so that we are in the form of a times 10 raised to power n. When numbers are written in that form, a times 10 raised to power n, such that a falls in between 1 and then and n an integer, we say that that number is written in standard form. So n should always be an integer, and integer are whole numbers 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, etc. And then this means the number a can be 1 or more than 1, but always less than 10. This means a can never be equal to 10 or more than 10. At the same time, a cannot be less than 1. If it is less than 1, we'll be talking of 0.9, 0.00 something or something like that. So our a must always be either 1 or more than 1, but strictly less than 10, not equal to 10. For example, from what we are having here, if we are having 12, what we simply do, that is 0.1, 2, 3, 4, 5, 6, 1, 2 kilograms. To write it in standard form simply means we are going to move this decimal place from where it is to between 1 and 2. Because if it comes to before 1, that will be 0.1. That will be less than 1. If it goes past 2, the number obtained will be 12. 12 is more than 10, and we need an a that is strictly less than 10. So what do we do? Let us move it. We move it through 1, 2, 3, 4, 5, 6, 7 steps. So we shall have 1.2. then times 10. Now, because we moved the decimal place 7 steps to come to between 1 and 2, we shall be having a 7 up there. But now, we need a sign. We moved the decimal point to the right so that 7 becomes a negative 7 kilograms. Now, look at this. In this format, our A, our A or our 1.2 is our A. We have our 10, this one. And our negative 7 up there is equivalent to the n we wrote there. Now let us check. We already said a must be either greater than 2 or greater than 1 or equal to 1, but strictly less than 10. We look at 1.2. 1.2 is more than 1. But at the same time, 1.2 is less than 10. So this is our correct value for A. And then when we check at the n, we have here the power of 10. We have a negative 7. A negative 7 is a whole number, and so it is an integer, meaning that that number is written to standard form, and that is our correct answer for the standard form. Now for the second one that we are having, 364 and all those 9 zeros after it, we still express it in standard form. Because there's no decimal point, we assume it is after the last digit. So we are to move it from that last digit to between 3 and 6. So what do we do? How many steps? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them. So we have 3.64, then times 10 raised to power 11 kilograms. So if we look at the 3, our 3.64 becomes the A, then times 10 raised to power n. So A here is 3.64, and our n is equivalent to 11. So 11 is an integer. An integer is simply a whole number, and so this is also correct. So that number is written in standard form. One simple thing that we are going to see is that if we are moving the decimal place to the left, the power of 10 will be positive. If we are moving the decimal place to the right, the power of 10 is always negative in an attempt of writing those numbers in standard form. So we are going to have a short break after this. pause, and then we'll get back and we'll do a few examples of the standard form, and then we shall introduce something very nice. Until that time, I wish you to stay tuned to Hope Channel Kenya. Continue being blessed. Do not go away. See you after the break. Dear viewer, I'm glad that you are still tuned to Hope Channel Kenya, our program of Knowledge Quest. Our subject is physics, and we are talking about measurement 2. Welcome back as we continue with our lesson for today. Shortly before we went for the break, we were talking about the standard form of numbers, and we had done a few examples. And we said that when we are writing numbers in standard form, it is more convenient for us to use or to express and to use in the calculations. We said that numbers are written in standard form when they are in the form of a times 10 raised to power n, whereby a is between 1 and less than 10, and our n is always an integer. If that is the case, the number is said to be in standard form. I want us to consider these examples, so we write these numbers in standard form. Write in standard form. So we shall have 4 examples. The first one, we have number 1, 2068.1. So B, we write this number here, 0.0061, and then we have C, 3401, and then we can have number D, we have 0.0962. We want to write these numbers in standard form. Let us look at the first one. For us to write 2068.1 in standard form, you know, this is 2068.1, and that number is way above 10, and so it is not in standard form. So the simple thing we do is moving the decimal point from where it is to between 2 and 0. So we shall move, this is 1, 2, 3 steps, so that we have 2.0681, and because we moved 3 steps, the power of 10 is 3 positive. Just that. So that number is written in standard form when it is that way. For the second one, the decimal point is here. We are going to move it to the right because we want it to fall between 6 and 1. So we shall move 1, 2, 3 steps, and that becomes 6.1 times 10 power negative 3. For the next one, it is a whole number. There is no decimal point. If that is so, we assume it is after the last digit we are seeing. So if it is here, we still move it to the, now between 3 and 4, we shall move 1, 2, 3 steps. We have 3.401 times 10 raised to power 3 positive. For the last one, we are seeing the decimal point. We move it to the right so that it's between 9 and 6. We have 1, 2. So it is 9.62 times 10 raised to power negative 2. The only important thing for us to remember is that as we are moving the decimal place, if we are moving to the left, like for the part number A and C, where we are moving the decimal point to the left, the power of 10 there is positive. And for the other two, B and D, we are moving the decimal place to the right. If that is so, then the power of 10 becomes a negative power. But for all of them, you will just see that the number obtained here, this is 2.06. 2.06 is between 2 and 3, so it is obviously more than 1, less than 10. 6.1 is also more than 1, less than 10, the same as 3.401, the same as 9.6162. The powers of 10, all of them are whole numbers, and so they are integers. So we can conveniently say that these numbers have been written in standard form. This will be a very important way for us to express answers later on in some calculations of some experiments that we are likely to do at the end of this topic. One more thing another way of expressing our answers, we talk of decimal places. Then we'll do mixed examples. So decimal places. Now when we talk about decimal places, we are only referring to the number of digits we see after the decimal point. The number of digits we are seeing after the decimal point. In this case now, a 0 is included. The number of digits after the decimal point. That is what we call the decimal places. So then that means we can only talk of decimal places for decimal numbers and not whole numbers. Whole numbers don't have decimal places, and we cannot talk of decimal places for whole numbers. So here we are strictly looking at the decimal numbers. You know, numbers can be categorized into different ways. We can have whole numbers, decimal numbers, fractional numbers, etc. So here we are strictly talking of the decimal numbers, and the number of decimal places is the number of digits after the decimal point. For example, if we have 3.426, after the decimal point we have 1, 2, 3, then we say that number is to 3 decimal places. If we have a number, say 2.1, after the decimal point we have only 1 digit, so it is written to 1 decimal place. If we have 0.0004, say 7, after the decimal point we have 1, 2, 3, 4, 5, it is written to 5 decimal places. So decimal places is quite different from significant figures. At the same time, it is quite different from the standard form that we have just talked about. We are only referring to the number of digits we are seeing after the decimal point. Ideally, now we're going to express the number into decimal places the same way we were expressing in the significant figures. Let's look at that first number there. Of course, now we know it is written to 3 decimal places. Suppose we wanted to write it to 1 decimal place. What do we do? If we are writing it to 1 decimal place, it simply means we want only 1 figure after the decimal point. So we shall be having 3 point. Now if we want 1 decimal place after that's 1 figure after the decimal point, we have a 4. We consider what is coming after 4. If it is 5 or more, we add 1 to 4. If it is less than 5, we just drop it. So we have 3.4 as the answer. We do not keep zeros for 2 and 6, because if we keep this 0 and the other 0, we shall be having 1, 2, 3. This is 3 decimal places, but we want a 1 decimal place. So those 2 zeros are not included. If we want the same to 2 decimal places, we shall be having 3.42. So we want a 4 and a 2. Now we, after 2, look at what is coming after it. We have 6. 6 is more than 5. So we add 1 to this, to that 2. So it becomes 3. So the answer becomes 3.43. This is an answer written to 2 decimal places. Or rather, we have 3.426 expressed to 2 decimal places. So again, here we don't keep that 0. That 0 is not included, because if we include it, then it will be significant, and we shall be having 3. It will be considered and counted in the decimal places, so we shall be having 1, 2, 3. That is why we do not include it in the what we have written or what we obtain at the end. So simply put, when we talk of the decimal places, we are referring to the number of digits we are seeing after the decimal point. They can be 1, 2, 3, etc. As many as space can allow, or as much as the calculation that we have done will entail or will give us in the calculation. Let's do an example of writing numbers in decimal places. We consider a rectangle. Consider the figure below. So the figure is a rectangle, and let the rectangle have the sides 0.02 meters by 0.34 meters, and we are supposed to find the area and express. Consider the figure below. Find the area and give the answer to 4 decimal places. So what do? We say we already know from measurement 1 that area of a rectangle is length times width. This will be equal to 0.34 times 0.02. When we do that, what do we get? We have 0.34 times 0.02. This is 0.0068. And the question requires us to give the answer to 4 decimal places. So we count. We have the first, the second, the third, the fourth. So the area remains the way it is, 2 square meters. So that is the answer. Now suppose we were to give the answer, this, let that be Roman 1, Roman 2, to 3 decimal places. Already we know that the calculation when you do is 0.0068 to 4 decimal places. Now to 3 decimal places we shall count 1, 2, 3. So we stop at that. We consider the next one. If it is 5 or more, we add 1. This is 8. 8 is more than 5. So we shall add a 1 to the 6. We get 7. The answer becomes 0.007 square meters. Again, we don't put a 0 for 8 because if we have a 0 there, that 0 will be counted in the decimal places. The answer will be 1, 2, 3, 4. So we have to drop it completely. We do not include it in what we have obtained. If we were to give the answer to 1 decimal place, this is 3. 1 decimal place, we just come here. This is 0.1 is this first 0. Then we consider the next one, which is also a 0. If it is less than 5, we don't add anything. The answer becomes 0.0 square meters. So that is again what we are having from there. Decimal places are among the simplest things you can do in the calculations because you only count the number of digits after the decimal point. There is nothing much for you to do after you have done the calculations. Now I want us to consider a few examples of mixed concepts, still now using the 3 of them together. Examples. Express the following to Roman 1 4 significant figures. Roman 2 2 decimal places. Roman 3 standard form. And so the first number that we are going to have here is 4689.26061. We first express the number to 4 significant figures. To 4 significant figures, we already said we only count the numbers from the left, so we shall be having 1, 2, 3, 4. Then we consider what comes after the 9. This is 3. 3 is less than 5, so we drop it. In its place, we put a 0. So Roman 1, the answer for Roman 1 becomes 4689. 0. We stop there. We don't put zeros after the decimal point because the moment we put them, they are going to be significant and they'll be counted, and so the number will change from 4 to a different thing. So we have 46890 in significant to 4 significant figures. Roman 2 to 2 decimal places, we shall be having 46893.2. So we count 2 decimal places, the first one, the second, the other one is a 1. 1 is less than 5, so we drop it. So we have 0.26. Then the answer for in standard form, we shall be having the decimal point is here. So we move it to between 4 and 6. It will be, we move 1, 2, 3, 4 steps. So this becomes 4.6893.261 times 10 raised to power 4, because we moved 4 steps, 1, 2, 3, 4. And when we are moving to the left, the power of 10 is always positive. So we have that number in standard form. So it will be important for us to know this. Beyond here, when we'll be doing calculations, at some point we'll be required to express the number to a given number of significant figures, or to a given number of decimal places or to express the answer in standard form. It's always good for you as a student now, when you'll be answering questions regarding calculations, to be very keen on the terms used there as far as how you are going to express your answer. Getting the answer in a calculation is not enough. Expressing it the way it is required is more important, because marks will be awarded depending on whether you expressed it in the correct form and not necessarily getting the correct calculation. So you have to be very keen with the significant figures, the decimal places, and the standard form of numbers. Ideally, we may not have new calculations to do. It's only to express the answers for the calculations we did in measurement 1 in these 3 forms that we have listed here. So what have we learned today? We have talked about the significant figures. I wish that you as a student now go and do more practice on the significant figures, and particularly the significance of a 0 when it is used in a number. We already said if it is to the left of a number, that 0 is not significant. If it is between and 0 digits, it is always significant. To the right of a whole number, it is or it is not significant. It depends. To the right of a decimal number, the 0 is always significant. But the rest of the non-zero digits are always significant if they appear in a number. For the decimal places, we're referring to the number of digits after the decimal point. Even if it is a 0, it is always counted. So it is the number of digits to the right of a decimal point, including a 0. So there is no special treatment for the 0 in the decimal places. It is also included and counted. For the standard form, it is what we already said. You express it in the form of a times 10 raised to power n, whereby this is between 1 and less than between 1 and 10, but always less than 10, and n an integer. Now in our next lesson, we are going to explore some more information concerning measurement 2, and we're going to look at the oil drop experiment. We're going to do some calculations there, and we shall be requiring this information. I wish that you continue practicing, remain and stay tuned to Hope Channel Kenya. Hope Channel Kenya should be your home of blessings. Continue watching other programs until we meet again for our studies. For the next subtitle, I pray that God may keep you safe, may protect you, bless you until we meet again. Stay tuned, remain blessed. Goodbye.